Hello all, my name is Krishnayak and welcome to my YouTube channel. So guys, if you are actually following my complete deep learning playlist, I had discussed about some of the activation functions like Sigmoid, TANH, Relu and leaky Relu. But they are still different variants of Relu, and apart from that there are also other activation functions which are pretty much important. So in this particular video, I have made a long video of more than 35 minutes, to make you understand all these things. Yes, and I've discussed in detail, in depth about Relu, Riki Relu. We have discussed about Elu, right? This is basically the exponential linear unit. Then we have PRelu. Then we have Softmax activation functions. As we say, guys, in the last layer, if it is a classification problem, if it is a binary classification problem, at that time we actually use Sigmoid, right? And if it is a multi-class classification problem, we basically use as a Softmax. But how does Softmax actually work? There is also an activation function which is called as Swish, which has been come out from Google Brains. They have actually invented this activation function. And apart from that, we also have an activation function which is Softplus. Again, it is a kind of variant of Relu itself. So all these things will be discussed in this particular session. Again, I'm saying you guys, this session is going to be a little bit big, more than 35 minutes, where I'll try to show you and show you most of the things and try to explain you. So please make sure that you watch this video till the end. This video will be the part of the deep learning playlist, and if you go and check out the deep learning playlist, I'll also put this video in the proper order, soon after the Relu and leaky Relu is done, because this particular video has some more added activation functions. Now the reason why I'm uploading this video is because these videos were missed in the deep learning playlist. There is also an optimizer that we missed, that is called as Adam optimizer, that will come after this particular video is actually uploaded. So that recording has also been done. So probably tomorrow that particular video will be done. So please do enjoy this particular video and please do watch the whole video because I have explained it properly. So let's go ahead. Okay. We have discussed about sigmoid function, right? In sigmoid function, I told you that our value will be ranging between 0 to 1. Okay. That basically means whatever weight. So after this calculation goes on, right, we apply a function on top of it. That function, for in our case, we are going to take sigmoid. Once we do this, that is weights multiplied by the input plus bias, right? This is my bias, right? After this, on top of it, we apply a sigmoid activation function. Once we apply sigmoid activation function, the value that we get is between 0 to 1. But sigmoid, what I told that whenever I try to find out the derivative of sigmoid in the back propagation, the value will be ranging between 0 to 0.25. These all things have been covered in our previous class. Okay. Then I also told that what is the major problem with respect to sigmoid function? When we are doing back propagation, there is a concept called as vanishing gradient problem. Vanishing gradient problem, right? That basically means the weight updation, right, is getting updated by just a small number, which is very, very negligible, right? And these all things we have discussed it. I would suggest, guys, go through our previous tutorials, because if I start explaining again, it will take time. Then we understood some about, see, prone to vanishing gradient. Function output is not zero centered. Now, what does this not zero centered basically mean? Not zero centered. Remember, guys, this not zero center means what? Now, if I take a normal distribution data, right? If I take a normal distribution, suppose this is my feature. If I'm taking a normal distribution says like this, okay? Here, my standard normal distribution, suppose I feel like standard normal distribution, okay? Now, when I take a standard normal distribution data, you would know that my mean is 0 and my standard deviation may be something. In case of standard normal distribution, my standard deviation is basically 1. So my data is basically centered between 0, okay, and it may be either positive, it may be either negative, okay. So this is what it basically says. This is the meaning of this is what is the meaning of if I take my function output is 0, I can say that this data is basically 0 centered. I can say this data is 0 centered. Why it is 0 centered? Because understand over here, 0 centered basically means what? I'll tell you, because this is very important to understand. Suppose my data is present with a some mean is equal to 0, like this over here, and standard deviation is equal to 1, or it may be some other small number. You will be seeing that most of our data will be either positive or negative, but it will always be in this specific region, which is centered towards 0. Okay. But in our case, if I go and see if I go and see this particular sigmoid function, it is obviously not centered towards 0, right? You can see that most of the data over here, it is basically ranging, other data is basically ranging over here. But in this function, whenever we say that it is having 0 centered, data is basically 0 centered, we basically talk about this kind of bell curve or Gaussian curve. Okay, so in short, if somebody asks you what is the most specific thing about normal distribution data or Gaussian distribution data, at that time you can specifically say that the data is zero centered. But in the case of sigmoid, it is not zero centered. Now, why this may play a very, very important role, just understand that if the data is not zero centered, more computation time will be taking up, and because of that, to reach the convergence point, that is the global minima, also it will take time. Okay, so this was the point that I missed when I was explaining about sigmoid. Okay, so guys, and any queries that you have, just note down in your notebook, and at the last we'll try to solve that particular queries. Okay, now coming to the tanh function, I told you in tanh the output of your x, that is basically your weights multiplied by the x plus bias, right? Whenever I try to provide that particular output, that value is ranging between -1 to +1. Okay, and when I try to find out the derivative of those, the value is between 0 to 1. Okay, and again, you also have a vanishing gradient problem over here. Okay, it is almost like sigmoid, but just remember the range is different. Okay, and here also your data is not zero centric. Okay, so here you'll be able to see, sorry, this data is basically zero centric. You can see that it is ranging, it is coming from here, it is going to this zero centric, and it is coming over here. Okay, so here you can see, over here you cannot see that it is zero centric, because now none of the data passes through this zero. Any data that passes through zero, any data that revolves around zero, is basically called as zero centric. Okay, in this particular case, here also you can see that all your data is ranging between -1 to +1, but most of the data passes between this 0 and this particular value, so it is zero centric. At one point of time, you'll be seeing that it is reaching 0. Okay, so here you can see that it is also written the output interval of tanh is 1, and the whole function is zero centric, which is better than sigmoid. This is obviously better than sigmoid, but one problem that we face with respect to tanh is basically the vanishing gradient problem, because your derivation of tanh is always ranging between 0 to 1. Okay, now coming to the Relu activation function. Now in Relu activation function, you can see that the functionality was max of 0 comma x, right? Max of 0 comma x. Now this basically says that whenever your x value is greater than 0, then the output that you're going to get is basically that particular x. If your x value is less than or equal to 0, you are basically going to get the value as 0. Okay, now remember, when I try to find out the derivative, with respect to x, if I try to find out the derivative with respect to x, this x, derivative of x with respect to x is what? 1 only, right? So all the derivation will be 1. Whatever the x value is greater than 0, all the derivation will be 1. Whenever the x value is less than or equal to 0, you will be finding it is as 0. Okay, because this is a constant, right? This is a constant over here. Any value that you're going to try to find out, it will be constant. But again, you have one condition, that you cannot, in the real world scenario, you cannot find out the derivative of 0, right? So for this, how do we handle it? I'll just tell you. But remember, this derivative of x, you will not be able to find out. I'll just talk about it in a practical scenario. Okay, now see this. Now what happens? Whenever your x value is less than or equal to 0, you will be getting it as 0. But I told you, what are the main problems with respect to this? When you are doing the back propagation, or whenever you are doing the back propagation, that time, whenever you are trying to find out the derivative of a negative weights, suppose you have some negative weights over there, right? And whenever you are trying to find out the derivative, this is going to be 0. And when 0 is there, according to the chain rule, right? According to the chain rule, right? Suppose one of my derivative is 0, the other may be 1, the other may be 1, like this, right? Because it may be either 0 or 1. So whenever there is a 0, this whole value will become 0, right? And when you are doing an weight updation formula, like W is equal to W minus learning rate of derivative of loss with respect to derivative of W old, right? This is my W old. Now, when this value is becoming 0, right, this whole value will become 0. At that time, your weight new will be equal to weight old. So in this particular case, the weight updation will not happen. And this scenario is called as dying Relu or dead activation function. Okay, dying Relu or dead activation function, right? Now, in order to prevent it, I told you that this is the problem with respect to Relu. Relu is the most common activation functions used in hidden layer. Okay, it is used in hidden layer. Why it is used? Because it solves the vanishing gradient problem. First of all, it solves the vanishing gradient problem. How does it solve? The derivative of a Relu function is either 0 or 1. Okay, and remember, it is not between 0 to 1. It is either 0 or either 1. Whenever the x value is greater than 0, it will be 1. If it is less than 0, it is going to be 0. Okay, but whenever we have this 0, we have this dying Relu condition. I hope everybody knows from my previous session. If you have not seen the previous session, you will not be able to understand this, guys. Okay, I have clearly mentioned, I have clearly explained in this all things in my previous session. I'll just show you that also, where I had written all the things. If you have to really check out the video from the previous session, whatever has been uploaded. Okay, now this was the thing with respect to Relu. Now coming to the next thing, if I talk about leaky Relu activation function. Now here you see, in Relu, max of 0 comma x was there, right? Max of 0 comma x was there. That basically means if your x value is greater than 0, then that basically means that will be selected as a max value. But in this case, I told you that my derivative doing the back propagation is basically bringing us 0, and it is showing us a dying Relu or dying activation function, because if the derivation is 0, the whole value is actually becoming 0. So in order to prevent this, we will be using leaky Relu. In leaky Relu, we will be multiplying a small constant with x. Okay, with x. Again, see guys, over here, we will be multiplying a small constant with x. Okay, so whenever your x value is basically a positive number, it will be coming up that. Now see this will be very interesting. If I try to find out the derivative of x with respect to x, this will definitely give me 1. So these all values will be giving me 1. If I try to find out the derivative of 0.01 x with respect to x, at that time, what value it will be giving me? It will be giving me 0.01. So instead of having a smaller value, a smaller, lighter value on the top of that line. See, initially, if I just go on the top, right, my derivative over here was exactly 0. But in order to solve the dying Relu problem, now instead of 0, it is showing us 0.01, right? So this value that you see from the y-axis, it is basically getting combined over here. It is combined over here, and this is my value as 0.01. So this is actually solving my dying Relu problem, because whenever my values are negative, okay, whenever my values are negative due to negative weights, when I do the derivative of this value, it is going to come it as 0.01. Now this 0.01 is greater than 0. So in this particular case, my whole derivative of loss with respect to derivative of w will not be equal to 0. It will be greater than 0, because this value, instead of multiplying with 0, we are multiplying with 0.01. Okay, so that is how we are solving this dying Relu or dead activation function. Okay, by just multiplying a constant along with x. Initially, in a normal leaky Relu, it was 0 comma x. Here we are having 0.01 multiplied by x, because when we do the derivative with respect to this particular function, I am either going to get 1 or I am going to get 0.01. Okay, so because see this is 0.01, because whenever I get this particular value, I'm trying to find out the derivative with respect to this. Okay, so with respect to that, I'll be actually showing it. So this was with respect to leaky Relu, and this also I discussed it. This also mathematically we discussed it. We try to understand. And guys, I'm still revising, previous concept. Don't think that I'm teaching something new. These all are all previous concepts that we had already discussed. Okay, now coming to the next one. Now, fine. With respect to leaky Relu, I told her that for negative value, we have at least something like 0.01. Okay. Let me just show you here. I think we had discussed it here itself. Let me just upload it. Okay. Now see, whenever we have this kind of derivative, okay, this is your sessions only what I had actually discussed. Whenever we are trying to find out this kind of derivative, I told you that if I'm using leaky Relu, for some of the weights, if they are negative, right, that may come as 0.01. Okay. 0.01. So I may use it as 0.01 over here. Suppose this particular value is 0.0. This value is 0.01. Okay. This value is 1. Okay. Then again this value is 1. And again this value is 0.01. And sometime it may happen that it may be becoming less than 0.01 when we are going through the back propagation in a deep layer. But whenever we do this kind of multiplication, right? Whenever we do this kind of multiplication, will this be a small number? Will this be a small number? Obviously, the answer is yes. So usually what happens is that whenever we are trying to use leaky Relu, there are chances of vanishing gradient problem to happen. Vanishing gradient problem to happen. Because if suppose most of my weights are negative, if most of my weights are negative, maximum number of weights are negative, that time in with respect to the derivative, I will be multiplying with 0.01, 0.01, 0.01 everywhere. And because of this, this will definitely become a smaller number. If this becomes a smaller number, this will also become a smaller number, right? So when we are updating along with the learning rate, our W new will be approximately equal to W old. So definitely in some of the scenarios, it has been said by the researcher that leaky Relu actually brings up, this kind of vanishing gradient problem. Okay. So we'll try to understand what is the next thing that we can bring up. Now we are coming to the next activation function, which is called as Elu. Elu basically says, which is called as exponentially linear units. Okay, exponentially linear units. It basically says that what we are trying to do with respect to Elu, instead of whenever your x value is greater than 0, see again, it will be exactly same. Only they are trying to handle the negative values in an efficient way. Whenever your x value is greater than 0, your output will be always x. Whenever your x value is less than or equal to 0, then they are basically applying this particular operation. That is alpha e to the power of minus x minus 1. Okay, this alpha will be a learning parameter also. We can say it as a learning parameter, or it may be some fixed parameters. We have to put this like 0.01, 0.1, 0.2, 0.3. So this depends on different kind of problem statement. This is basically a hyperparameter. Okay, hyperparameter. So when we fix some alpha values, if I try to see the diagram with respect to Elu, right, the exponential linear units, your layer will look something like this. Your layer will look something like this. So this is how your data will be looking. This is not a Relu, or this is not a leaky Relu in short, right? In leaky Relu, I told that my data will be looking something like this, right? It will be something like this, a small value of 0.01, right? In this case, you're having like this. Okay, now what kind of problem it is actually solving, we'll just try to discuss it. Okay, and whenever I try to find out the derivative of this kind of value with respect to this function, I will be getting this one. Now here you are solving one major problem, that you don't have to find out the derivative of 0, because and nowhere you are getting derivative of 0. Okay, because here whenever you are trying to find out the derivative, you are getting this kind of curve. Okay, whenever your x value is less than or equal to 0, you are actually getting this kind of curve. So the major problem that you're solving over here obviously is that you are not have to find out the derivative of 0 in this case, because that value will always never come. If I go and see other values, right, suppose what happens if my x is 0, in this also I'll be getting this 0, or it will be very very near to 0. In this particular case, it will be exactly 0, right? So whenever I'm trying to find out a derivative, obviously you cannot find out a derivative with respect to 0. Apart from this also, there is also one more function which we'll discuss about that. But just understand that this exponential Relu is actually for fixing this problem. Let us see what all problems it is other than fixing that. Okay, so if I go down, Elu is also proposed to solve the problems of Relu. Obviously, Elu has all the advantages of Relu. Obviously, you can see. Always remember, you have to see this function and you have to see the derivative function. Okay, no dead Relu's issues, first of all, because again, in this particular case, all the time you are getting some positive number. Okay, here also you are solving the dead Relu issues, because in the derivative, none of the values exactly 0. This is little bit more than 0, guys. Okay, it is just above the line. Don't consider that this line is actually showing you 0 value. 0 values basically means with respect to y-axis, the derivative values. Okay, we are trying to find out. The mean of the output is close to 0 or 0 centered. So this also functionality is basically been implemented, that the mean value is basically zero centered because it is passing through zero. Most of the data is passing through zero. Whenever any curve that you create, if it passes through zero, it is basically said as zero centered data. Okay. One small problem that is slightly more computational intensive, similar to leaky Relu. So guys, remember, this is a function e to the power of minus x minus 1. Whenever we do back propagation to find out the derivative of this particular value, since it has exponential term, it will definitely take time, because derivation, see, one thing, if I try to, if I, sorry, just a second. If I try to find out the derivative of x with respect to x, this will obviously take very less time, right? It will obviously take very less time because we are just trying to find out with respect to a variable. Now, what if I try to find out the derivative of alpha e to the power of minus x divided by derivative of x? In this particular case, since we have an exponential term, that's there will be some time taken for this kind of operation, because there is an exponential term, there is some alpha value, and with respect to x, this will obviously take some amount of time, right? Because this is basically taking less time, this is taking more time. So we basically say that ilu is basically computational, it requires more it is computationally expensive. Okay. Similarly, in the case of tan h also, it is computationally expensive, because in tan h, there you will be seeing that you will be finding out the derivative with respect to a tan h function, right? So always remember this computational derivative with just with respect to one weight updation, definitely will not be looking at. But when you're creating a neural network, there'll be so many hidden layers. There'll be so many hidden layers. There'll be so many weights, right? There'll be so many weights. In that particular case, we require very, very good. And in this particular case, you can see that whenever you're applying an Elu activation function, you will be seeing that one major disadvantage is that it is computationally expensive. Now, the other thing, that what type of problem it is solving, we have already discussed that it is solving dying Relu problem, drying Relu activation functions. And then it is also solving one more. It is also solving, it is basically saying that all this data are zero centric. Okay. So remember, whenever you want to explain regarding activation functions, you have to basically say all these things. Now, we'll discuss about Softmax, but before that, let's discuss something about PRelu. Now, in PRelu is an activation function, and this is called as parametric Relu. In parametric Relu, all the functionalities will be same. All the functionalities will be same. Okay. What do I mean by same? Whenever your x value is greater than 0, okay, it is going to give you the x. Okay. Then, whenever your x value is less than 0, you will be given some alpha multiplied by x. Okay, remember this. This is what this particular function says. Okay, whenever your x value is greater than 0, it is always going to give you x. Whenever your x value is less than or equal to 0, it is going to give you alpha multiplied by x. Now, see over here. Very, very nice concept. Okay, if your alpha value is equal to 0.01, see over here, if your alpha value is equal to 0.01, this will actually become leaky Relu, right? See this first one, if your alpha value is 0.01, it is going to become leaky Relu, because if I become leaky Relu, it is nothing but 0.01x, right? If your alpha value is 0, that basically means this becomes Relu, right? It becomes Relu activation function. It becomes Relu activation function, because if I make your alpha value as 0, 0 multiplied by 0 will be, 0 multiplied by x, it will also be 0. So in this particular case, the whole value will become 0. So this will be like a Relu activation function. The third criteria is that if you place alpha with respect to any value, okay, alpha with respect to any value, then you will be able to solve any kind of problem. So this alpha can be considered as a learning parameter, which will dynamically change based on the learning, based on this particular activation function. This alpha is not fixed, because with respect to different hidden layers, with respect to different activation function, this alpha value may change. Okay, so this is a learning parameter. Okay, learning parameter, all the time it will not become 0.01, because whenever I use leaky Relu, this value will definitely become 0.01. If I use Relu activation function, this value will become 0. But in some of the scenarios, we may use different activation function with different alpha values. At that time, this will be dynamically learned when the training is actually happening. Okay, so I hope everybody's clear till here. Okay, so parametric Relu is solving both leaky Relu problem statement, normal Relu, and different kind of Relus. Again, Relu, these all are variants of Relu, guys. Different variants of Relu, right? So here you can also see this. So let's discuss about this. Pre-Relu is an improved version of Relu. In negative region, pre-Relu has a small slope, which can also avoid the problem of Relu death. So whenever I'm telling you this one, sorry, this function is not there. Whenever I'm trying to multiply it by alpha of I, that basically means that this alpha of I, obviously, when we are trying to use it as 0.01, it is always going to give me a derivative like this, right? It is going to give me a derivative like this, right? If I'm using alpha is equal to 0, at that time definitely it will become a Relu function and my derivative will be like this. But this problems has dead Relu function, right? Dead Relu, dead activation function. So this can be learned as, this can be considered as a learning parameter with respect to this. Okay, so here you can see if AI is equal to 0, F becomes Relu. If AI is greater than 0, F becomes leaky Relu. If AI is a learning parameter, F becomes pre-Relu. Okay, parametric Relu. Very much simple, very much easy. Okay, now coming to the next one, which is called as Swiss Relu. Okay, Swiss Relu. In this Relu activation function, the formula is only this much. Okay, y multiplied by sigmoid of x, and this is called as self-gating. This is used in LSTM. Okay, LSTM mostly. This is very computive extensive, guys. And remember, this kind of activation function you use only when you have in your neural network greater than 40 layers. Greater than 40 layers. Whenever you have greater than 40 layers, minimum it should have 40 layers, then only this Swiss a self-gated function will work. Otherwise, if you are having less than 40 layers, this is definitely not going to work. Okay, now let's go and understand the maths behind it. Okay, the maths is pretty much simple. Okay, remember, guys, this color, in the pink color you see, this is a Relu activation function. Okay, but in the case of Swiss, the function that you're going to create is nothing but x multiplied by sigmoid of x. What is this x? X is nothing but weight multiplied by the input plus the bias, right? So this is what you are actually getting, and because of this you are getting this kind of curve. Okay, this curve is pretty much good. It is also zero centric because it is passing through zero. It is also solving the dead neuron problem, dead Relu problem. Why? Because whenever I try to find out the derivative, this is going to give at least greater than 0. Okay, whenever we are trying to find out the derivative, it is always going to give me 0, because when I try to find out the derivative with respect to sigmoid of x, with respect to x, I'm also going to get different values. This will definitely give me 1. This will give me based on this x equation, right? Whatever x value I have, and with respect to the sigmoid. So whenever I try to find out the derivative, it is always going to be a little bit greater than 0. So this is called as a self-gated function. Okay, self-gated function. Again, you can see, guys, there are so many activation functions we have discussed over here. Only the thing that is mostly focused on is in this particular negative value. So that is the reason why in my previous session I discussed about so well with respect to vanishing gradient problem, exploding gradient problem, how to solve that, how to fix that. Okay, so this was with respect to this one, which is called a self-gated function, which is nothing but a Swiss function. Now coming to the next part, which is called as max out function. Okay, let's read about it. Okay, again, guys, you always have to read this. Swiss design was inspired by the use of sigmoid function for gating in LSTM and highway networks. We use the same value for gating to simplify the gating mechanism, which is called as self-gating. The advantage of self-gating is that it only requires a simple scalar input, while normal gating requires multiple scalar input. The feature enables self-gated function as to easily replace activation function that takes a single. But remember, guys, this I talk about unboundedness, but remember just like this, that whenever you have a deep neural network, at least more than 40 layers, you should basically use a Swiss self-gated function. Now coming to the next one, which is called as Softplus. Okay, now in Softplus, you can see over here, guys, I told you that derivative of 0 is sometimes not possible. in the real world scenario. Even though most of the things, whenever we are actually calculating, there are sometimes scenarios where you may get the value as zero, the x value as zero. Not most of the time, but at least it is a rare scenario that you will be getting the value as zero. If you get in that specific way, definitely using a Relu activation function will not serve the purpose, because you don't know the derivative of zero. Okay, so what we do is that we try to use a function which is called as Softplus. Now this Softplus function, you'll be seeing that the function looks something like this: log log to the base natural log to the bracket 1 plus exponential of x. So instead of applying max of 0 comma x, the function will basically apply this one, and because of that you'll be seeing that you'll be getting this kind of curve. And here both the problem will get solved when you're finding out the derivative, remember. And here you will be able to see that here derivative of 0 need not be found out in this particular curve, that is your green curve. And this is basically called as a Softplus activation function. Okay, so these were the different activation functions that we have discussed in today's session. There is also one more thing which is called as Softmax. Now in Softmax, let me just define it for you. Okay, so I'm just going to go over here and open this, okay, for today's session, and let me just define Softmax activation function. Okay, now remember over here, guys. First of all, suppose I have, this is my input layer, suppose this is my hidden layer, right? This is my, again, another hidden layer. And suppose I have 3 output layers, okay? Three output layers. What does Softmax basically say? Okay, what does Softmax basically say? Let me just show it to you. The Softmax activation function applies a simple formula. Whenever you remember, guys, whenever we have 2 output layers, suppose 2 output layers, at that time we use sigmoid activation function. I told you that, right, in my previous session. Whenever I have 2 output layers, we use sigmoid activation function, and we know that sigmoid activation gives us the value between 0 to 1. Now if there are 2 output layers, first of all, okay, let me just make this as 2 output layers initially. Let me make this as 2 output layers. Suppose this is my 2 output layer. Okay, this is my 2 output layer. Okay, so in this 2 output layer, since I'm using a binary classification, I'll definitely use sigmoid activation function. Now when I use the sigmoid activation function, suppose I get this probability. Suppose the image that I'm passing, suppose I'm passing the image of a dog or a cat. So my output layer will be that either it will be a dog or either it will be a cat. But with respect to sigmoid function, what happens is that it says me, okay, it is giving me, it is 0.60, that is 60%, it is saying me that it is a dog. 0.40% it is saying me that it is a cat. Remember, this is a classification problem, and this is working on probability. Okay, my model says that 60% it is saying that the image is a dog, 40% it says me that it is a cat, right? Now in this particular case, what we do, we say that, okay, whenever the value is greater than 50, we are going to consider that particular value, and we are going to say that that is the output, right? In this is with respect to sigmoid activation function. And when I try to find out the sum of these two values, remember, when I try to find out the sum of these two values, this value is going to become 1 or 100%, right? But now what if I have 3 output layers? I cannot use sigmoid activation function. Okay, sigmoid activation function is only going to give me values between 0 to 1. So whenever I have more than 2 output categories, at that time we use something called as Softmax activation function. Now what does this Softmax activation function say? Not only greater than 2 outputs, guys, greater than any, it may be any number of outputs, it may be 10 outputs, it may be 20 outputs. Suppose I suppose I have 4 outputs like this. Okay, I have 4 outputs, and I want to check whether this image belongs to a dog or a cat or a monkey or a human being. Okay, like this, what is I'm actually checking. Now suppose my first output Okay, internally I'm using Softmax, so this will actually give me probability like this. Now see this. Suppose I say my first output is 0.6. This is saying 0.6 it belongs to dog. The second output says 0.2 it belongs to cat. The third output says 0.1 it belongs to, you know, 0.1 it basically belongs to our suppose this is chimpanzee, something like that, and 0.1 it belongs to human being. Now in this particular case you will be seeing that you will be getting 4 different values, and always remember the sum of all these values will be 1. Okay, sum of all these particular values will be 1. Now if I really want to find out the softmax function of this particular values, it is pretty much simple. We basically apply a simple formula. Let me just show you the formula. The formula looks something like this: e to the power of xj divided by summation of k is equal to 1 to k e to the power of xj. Now what does this basically say is that, now I have written some probability values like 0 0.6, 0 0.2, 0 0.1, 0.1, right? I have written like that. I can show you. This is my final output. But before this, whatever x value we get, whatever x value, because see over here, we are just applying e to the power of xj. Xj is nothing but weight multiplied by inputs plus bias, right? Xj is nothing but that, right? Weight multiplied by input plus the bias. Now, suppose before this, I still did not apply a softmax activation function. And suppose my four values were like this. Suppose my 4 values were like 40, 30, 10, 5, right? If my values are like this, if I really want to find out what is this value probability with respect to softmax, so the formula will be like e to the power of 40 divided by e to the power of 40 plus e to the power of 30 plus e to the power of 10 plus e to the power of 5. This should be the formula. Sorry for that. In the case of softmax, this is basically the formula. Now suppose this value gives me 0.61, okay, or it may be giving me anything. Okay, e to the power of 40, you can do the calculation like this. Okay, e to the power of 40, what is e to the power of 40 divided by e to the power of 40 plus 30 plus this? It will give me some value. Okay, some value it will give me. Then if I really want to find out this one, so it will be e to the power of 30 divided by e to the power of 40 plus e to the power of 30 plus e to the power of 10 plus e to the power of 5. Similarly, e to the power of 10 divided by e to the power of 40 plus e to the power of 30 plus e to the power of 10 plus e to the power of 5. Like this, we have to actually compute. And that is what the formula says over here. Okay, e to the power of xj divided by summation of e to the power of k is equal to 1 to k e to the power of xk, where j is equal to 1 to k. Okay, so that basically means how many number of values that I am having before this layer, whatever values, whatever the output of this value, the output of, so that the input of this value, the input of this value, the input of this. So we are going to combine all this particular value and we are going to compute like this. And finally, you'll be able to see that you'll be getting some 4 probabilities. Here I've just taken as an example. You may get 4 probabilities, and whichever will be the highest probability, you're going to take that as our final output. Okay, final output. So this is called as, this whole thing is basically called as softmax activation function. Sigmoid and softmax activation function is always kept in the last layer. So I hope you like this particular video, guys. These were all the important activation functions, and you can definitely play with all these kind of activation functions. Probably in the next video, again, I'm also going to update the optimizers with respect to Adam optimizers. So yes, most probably the video will be uploaded tomorrow. So yes, this was all about this specific video. I hope you like it. Please do subscribe to the channel if you have not already subscribed, and share with all your friends whoever require this kind of help. I'll see you all in the next video. Have a great day ahead. Thank you, one and all. Bye bye.